Hello, this is part 3 of lecture 2 of linear algebra, and this part is about orthonormal basis and orthogonal decomposition. Let me remind that if you have two vectors in an n-dimensional space, if the dot product is 0, we say that these two vectors are orthogonal. And we can generalize this definition for many vectors. If you have m vectors in n-dimensional space, v1, vm, we say that they are orthogonal if dot product of any two different vectors in this list is 0. Yeah. Moreover, we say that these vectors are orthonormal if they are orthogonal and length of every vector in this list is 1. So this is basically this condition. Okay, so for example, if you take a standard basis vectors e1, en of n-dimensional space, these vectors are orthonormal. The dot product of any two different vectors in this list is 0, and ei dot ei is 1, which simply means that length of vector ei is 1. On the other hand, if you take these two vectors in Rn, then in R2, then these two vectors are orthogonal. You can just check dot product and you see that this is 0. But on the other hand, they are not orthonormal because length of none of this vector is 1. Okay. So the good thing, if you have orthogonal vectors, that it's very easy to check when they're linear independent. Basically, they always linear independent if you know that they are non-zero. This is not hard to prove. Basically, you have to use definition of being linearly dependent. So you assume that orthogonal vectors linearly dependent, and then you write down the expression that the linear combination is 0 vector, and then you take a dot product with each vector in the list, and this immediately gives you that all coefficients in this sum must be 0, provided that all vectors in your collection are non-zero. Basically, this is the sketch of the proof. We're not going to do it here, but I strongly suggest to prove this lemma by yourself. Again, this lemma says that if you have orthogonal vectors, and you know that all of them are non-zero, then they are automatically linearly independent. You don't need to check this. This is actually quite useful because usually if you have many vectors in some space, then it's not easy to check that they're linearly independent. For orthogonal vectors, this is almost automatic if you know that they are non-zero. But in one important case, we know that they are non-zero if they are orthonormal. So this gives you this corollary. If you have orthonormal vectors in n-dimensional space, they are automatically linearly independent. Okay, and we can use this to define what is known as orthonormal basis. This is one of the main definitions of this part of the lecture. So orthonormal basis of a vector space is a basis consisting of orthonormal vectors. Yeah. Okay, so unlike usual bases, we don't know that orthonormal bases always exist, but we know in some examples. For example, if you have standard basis E1, En, we already mentioned that this is orthonormal basis of Rn. But in general, this is a proposition. I wanted to say theorem, but I downgraded it to proposition. So which says that every linear subspace in Rn has at least one orthonormal basis. We will give a sketch of the proof of this proposition basically during this lecture, and we also will give the algorithm how to find some orthonormal basis if you know any basis, how to convert any given basis into orthonormal one. But detailed proof of this proposition is in the lecture notes. Okay, so we will use it, and we assume that every vector subspace of n-dimensional space has some orthonormal basis. Okay, why being orthonormal is important? Okay, let me give you some illustration of this. Let's fix some linear subspace of Rn, and suppose we able to find some orthonormal basis of this space V1, Vm. And then you take any vector in V, and we know that since V1, Vm is a basis of V, X can be represented as a linear combination of vectors in this basis. But in the orthonormal case, we can find this expression immediately. So again, let me stress here, this black box is a formula how to express immediately any vector in V as a linear combination of vectors V1, Vm. You have this formula. And okay, how to prove this? This is actually not quite complicated. So to prove this formula, you have to replace this x dot vi by lambda I, which you're gonna find. And then you just need to take dot product of the left-hand side and the right-hand side with v1, v2, v3, and up to vm. So for example, what happens if you take dot product of the left-hand side and the right-hand side with v1? On the left-hand side, you're gonna have x dot v1. On the right-hand side, when you take a dot product, all terms of the sum disappear except one, the one which contains v1. And then why? Because these vectors are orthogonal. And what is left? Is left is x is going to be lambda 1 times v1 dot v1. But v1 dot v1 is 1 because these vectors are orthonormal. Length of each vector in this set is 1. So you get lambda 1 equal x dot v1 as required. So yeah, okay. This is basically the sketch of this equality. I strongly suggest to prove this equality by yourself. This is not complicated, but when you actually prove it, you get a better understanding of what's going on. Okay, here's just one example. I took two vectors in R2 in the plane, V1 and V2. You can check that they are orthogonal to each other. Just take a dot product, you get 0. Also, you can check that the length of each of this vector is 1. So they are orthonormal. Since there's two of them, we know from the results of the previous part of this lecture that they form a basis. So they form orthonormal basis of R2. This basically means that every vector in R2 is a linear combination of these two. So for example, I grabbed randomly vector 5, 3. So 5, 3 should be linear combination of V1 and V2. The question is how to find this lambda 1, lambda 2. Again, you just take a dot product of left-hand side and right-hand side. And on the right-hand side, if you take dot product with V1, you get lambda 1. On the right-hand side, on the left-hand side, you get V5, 3 dot product with V1, which you can compute, which is 4 roots of 2. So you get the formula for lambda 1. Similarly, how to find lambda 2? You take dot product with V2. On the right-hand side, you're going to get lambda 2 because v1 dot v2 is 0, v2 dot v2 is 1. On the left-hand side, okay, here it's on the right, you're going to have vector 5, 3 dot v2, which is root 2. Okay, so this example is basically illustration of the proof of this formula. We will use this formula a little bit later in another slightly more general result. Okay, so let me just consider one bad example. So I randomly, absolutely randomly, took 3 vectors in R3 in 3-dimensional space in 3D, and I checked that they're linear independent and they span R3. So these 3 vectors, V1, V2, V3, is a basis of R3, some random basis. Yeah. And then I grab some simple looking vector 1, 0, 0, which is basically the first standard vector in the standard basis. But now it's just some vector, and I know that X is a linear combination of V1, V2, and V3. Yeah. Here, X can be represented as lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3. The question is how to find these 3 numbers. There are several ways of doing this. One way of doing this, you just compare the left-hand side and the right-hand side of this equality, the corresponding entries. and you make them equal to each other. This gives you three equations with three unknowns. Unknowns are lambda 1, lambda 2, lambda 3, and with some energy and time, you solve this system and you find lambda 1, lambda 2, and lambda 3. Another way, we can basically mimic the previous slide, what we did on the previous slide, in this setting for non-orthonormal bases. So we can just take a dot product of with vectors v1, v2, and v3 of this equality. You take this equality and you take a dot product with, for example, v1 with the left-hand side and with the right-hand side. And then you have this line, the first line. Yeah. And then you do the same with v2 and then v3, and you get this strange looking system of equations. But look, everything except lambda 1, lambda 2, and lambda 3 here is computable. Yeah, it's computed actually here. All these dot products can be computed. It's not hard. Yeah, so all of this dot products here are some numbers. Okay, actually these numbers. Yeah. So you put them back here. You have again three unknown, three equations, which you can solve with some time and energy. But just look, if these three vectors were orthogonal, then this system of equation going to be much simpler. Basically, this number going to be 0, 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 this and this. So you're going to have very simple system of equations. Yeah, but moreover, if these vectors were orthonormal, then this system of equation going to simplify much more. Everything except diagonal going to be 0, and on diagonal you're going to have lambda 1 here, lambda 2 here, and lambda 3 here, because v3 dot v3 is 1, v2 dot v2 is 1, v1 dot v1 is 1. So you solve it immediately. Actually, it's already solved for you. This is exactly what is proved on the previous slide. Yeah. Unfortunately, in this case, this basis is not orthogonal, it's not orthonormal, so the system of equations for lambda 1, lambda 3 is quite complicated. Okay, so the next slide is very important for basically some results which we're going to prove a little bit later in this course. And so it may look a little bit abstract, but I strongly suggest you just not to get confused. This is actually not so scary as it may look like. Okay, so let me just give a definition. So if we have a linear subspace in Rn, let's call it V, its orthogonal complement in Rn, usually denoted like this, V with this orthogonality symbol. It's pronounced like V-perp. Yeah, so this orthogonal complement to V, this is subset in Rn consisting of all vectors which are orthogonal to all vectors in V. Okay, so by definition, this is a subset in Rn, but of course, it's a linear subspace. This has to be checked and proved. This follows from this definition, but with some amount of work, which I strongly suggest to do by yourself, or at least read in the lecture notes. Okay, so, but you can use it for granted that orthogonal complement of a vector subspace is a vector subspace. Okay. Moreover, this definition can be simplified with the help of the following lemma. Namely, if you look at this definition, you see that basically by definition we have to check infinitely many conditions. So x dot v is 0 for all vectors in V. This is, I mean, a bit complicated. So, of course, this is a little bit redundant. Instead of checking infinitely many conditions, you can check finitely if you use this lemma. Namely, you took some vectors in V which span V. For example, the good choice is if you just took some basis. So, for example, here you may assume, if you wish, that V1, Vm is a basis of V. Yeah. So you take these vectors, and this lemma says that orthogonal complement can be defined as follows, or equal to the following set. all vectors in Rn which are orthogonal only to these vectors v1, vm. So instead of checking infinitely many conditions, you have to check only finitely many conditions, just m. You got m equations. Yeah, this is very handy because basically in all good examples, m can be chosen to be dimension of v, which is in most of examples not a big number, so you have just few equations. Yeah, so let me consider very simple example. It's so simple because I don't have enough space on the slides to put a big example, which we will do in the tutorial and the homework assignment. Okay, so you take just vector 1, 1, 1 in three-dimensional space. You take its span. What does it mean? Its span. It's basically all vectors that looks like lambda, lambda, lambda. Every coordinate is equal to the same number. Lambda, lambda is any real number, and this is span of this vector 1, 1, 1. Let's take its orthogonal complement. What's orthogonal complement? It consists of vectors x1, x2, x3, which are orthogonal to this vector. You just take dot product and you get this. So this dot product should be equal to 0. So orthogonal complement of v in R3 is given by this equation. We already met this vector subspace in the previous part of this lecture. We know it's two-dimensional subspace, and we know it's a hyperplane. Yeah, passing through the origin. Okay. Now let me consider some formula for some operation which we're actually going to be using later quite a lot, and it's a standard exercise for a tutorial, homework assignment, or maybe exam problem. So, okay, it's called orthogonal projection. So first, let me fix some linear subspace in n-dimensional space, and let me take some orthogonal basis of V. We know it exists. Yeah. Then for every vector x in Rn, we can define vector p of x, which is given by this formula. So it's basically sum of vectors vi multiplied by x dot vi. Look, this formula is very simple to the formula which we saw on the previous slide. Yeah. So look, if very special case, if v is equal to Rn, just think about this. If v is equal to Rn, then this v1, vm is by assumptions orthogonal basis of Rn. Then we know from the formula on the previous slide that this sum is x. Yeah, this doesn't contradict anything. Why? Because of the following lemma. So this vector p of x has the following two properties. So first of all, this vector is contained in V. This follows from the fact that it's a linear combination of vectors v1, vm. v1, vm are contained in V, so the linear combination are also contained in V. So this first property is quite easy to check. The second property is more complicated, that the difference between x and p of x is actually contained in orthogonal complements of V. How to check this? Actually, implicitly, we already checked this in the case when V is Rn. Again, imagine that, suppose we know that this is true. So look, take a special case, V equal Rn. So if V equal Rn, what is orthogonal complement to V? It's orthogonal complement to the whole Rn. It's 0. It's a 0 vector. There's only one vector in Rn, which is orthogonal to all vectors in Rn. It's 0. So then in this special case, this lemma says that x equals p of x. So it means that x equal this sum in this special case when V equal Rn. But we already know this. We already proved this one slide ago. So this basically means that we can use the same proof to prove this lemma. Indeed, if you just take x minus p of x and just take a dot product with V1, and you get 0. Absolutely like in the case of proving the formula on the previous slide. And then you can take a dot product with V2 of this guy, of this vector, and you get 0. And with V3 and up to Vm. So it means that this vector is orthogonal to V1, V2, Vm. And so, by the lemma on the previous slides, it's orthogonal to the whole V. Okay, the proof is actually here. Okay, it's maybe not easy to read because it has a lot of the sums and something, but it's basically, the proof is exactly what I said. My strong advice, don't look at this proof, try to prove it yourself, and then read the proof. Okay, now let us define orthonormal extension. So what it is. So it's basically similar to extension lemma, but for orthonormal vectors. So we fix a linear subspace in n-dimensional space in Rn, and we fix some orthonormal vectors in V. We don't assume now V1, Vk form an orthonormal basis of V. We just took some collection, some list of consistent of orthonormal vectors in V. And then this extension lemma says that there exists some orthonormal basis of V which contains V1, Vk. So in particular, this lemma immediately implies the existence of orthonormal basis, which we mentioned a little bit earlier today. Okay, so for example, how to prove this? How to prove that this lemma implies existence of orthonormal basis? Okay, we need to start with some orthonormal collection of vectors in V. But for example, we can take one vector. Let's just take one. If V is a zero subspace, there's nothing to prove. Yeah, so we have to basically avoid this case. So suppose that V is not a zero subspace, then it has contains at least one non-zero vector. Take this vector, so maybe call it x. Then scale this vector, multiply it by some number, which is basically 1 divided by its length, such that the resulting vector has length 1. So if you have vector of length 1, it's automatically orthonormal. If it's just one, if your collection of vectors consists of one vector, there's nothing to take dot product with except itself. Yeah, and then you can apply this lemma and you construct orthonormal basis of V which contain this vector V1. And then you get, this proves you that vector V in particular has some orthonormal basis, as we claimed already earlier. Okay, so here is the proof. So let's look at the proof a little bit. It's in more details. This proof is contained in the lecture notes, but anyway, let's take a look here. So we have two cases here. So if K is equal to dimension of V, then we're done. There's nothing to prove. We already know that V1, Vk are linearly independent. And by some result we mentioned earlier, that orthonormal vectors always linearly independent. So the only question is when they span V. So if K is equal to dimension of V, we already know that they span V, and this case is done. So we may assume that K is less than dimension of V. Okay, so it basically means there is some vector which is in V, which is not contained in the span of V1, Vk. Let's call it Y. So this vector Y, yeah. And then we take this. We already know that this is orthogonal projection of vector Y to this span. Yeah, we have this vector. By definition, this vector is contained in the span of V1, Vk, and its difference Y minus W, it's orthogonal to this span. So it means that by the previous lemma on the previous slide, Y minus W orthogonal to this span. But this is, it looks like it's exactly what we're looking for. We want to extend this vectors to a basis. So we didn't extend yet, but we get some vector which is orthogonal to them. It's not zero by assumption, because Y minus W is not equal to 0. And so we already know that this new vectors, v1, v2, vk, y, they're linear independent. The question is, are they orthonormal? The first k definitely are, but the last vector may have length different from 1. So you scale it like this. You divide the vector y minus w by its length. So this vector now, it's basically the same vector as y minus w, but it has a length 1. You just scale it. And now you call it vk plus 1. You add it to the list. It's the collection v1, v2, vk plus 1. It's consists of orthonormal vectors. Now we know is it a basis or not, but we can repeat this process. We just can repeat this process and add next vector and next and next, and this process must terminate because we cannot have infinitely many linear independent vectors. At some point, we have to get basis of vector space V. This basically proves this lemma, and it also proves the proposition we mentioned earlier, that every vector has a orthonormal basis, at least one. Okay, good. This proof actually gives you an algorithm how to find orthonormal basis of every given vector space. But it may be a little bit sketchy and too abstract. Let me consider one example of basically the same algorithm, how to convert a given basis into orthonormal one. This algorithm is called Gram-Schmidt process. So this can be done for any basis of any vector subspace. But for simplicity, just in this example, I decide just to take R3 and take some basis of R3. Of course, this is not standard basis because standard basis already orthonormal. So, okay, so let me just take 3 vectors in R3. One can check that they form a basis. Yeah. We're not going to do this. Let's just trust it. So now you want to find orthonormal basis of R3. Of course, we know that standard basis of R3 is orthonormal, but this is illustration of this Gram-Schmidt process, illustration of orthogonalization process, how to find orthonormal basis of any given linear subspace. Usually you find some basis, and then you convert it into orthonormal basis using this algorithm. So we want to convert this basis into orthonormal one. Okay, good. So we start with vector u1. Okay, it doesn't matter from which vector to start. u1 was the first, you start with u1. You called it w1. Yeah, so first basically you convert your vectors into orthogonal vectors. And then once you get orthogonal vectors, you easily can cook up out of them by scaling orthonormal. So let's do this in example. You take vector u1, the first, and you call it w1. Fine. First step is done. Then you need to find the second vector. Let's call it w2, which is orthogonal to w1. How to do this? Okay, you first of all you define it as a combination of u2 and lambda times w1. So basically, think about this. First, you may take lambda to be 0. Just to try. Take w1, w2 equal u2. You want w2 to be orthogonal to w1. Okay, if u2 is orthogonal to w1, then you're done. But it may be not. So if not, you slightly change it. How to change it? You add to u2 this lambda times w1. Lambda is some number. Okay, the goal is to find the lambda such that this vector is orthogonal to this vector. Okay, how to check it? Just take a dot product. This is what we want. We want w1 dot w2 to be 0. Take this dot product. This is the same as this, the same as this. But now look, this number you can compute, and this number you can compute. So what you get, just 3 plus 9 lambda. So if you take lambda to be -1/3, you get this vector, and you know for sure that this vector is orthogonal to W1. Okay, now you have two vectors, W1, W2, which is orthogonal, and they basically obtained from the two vectors in our original list. Yeah, now we need to find the third one. You do absolutely in the following way. We basically already replaced first two vectors by orthogonal, and then we have to replace the third one. Yeah, by construction, W1.W2 is 0, but you can check W1.W3 is not 0 and W2.U3 is not 0. So, for example, if this vector U3 is orthogonal to the first two, we're done, almost done. Yeah, but it is not. So we have to adjust it absolutely in the same way how what we did with vector W2. You have to take vector U3 and you add W1 and W2 scaled by some numbers. Yeah, so what you do, you replace vector U3 by vector W3 that looks like this. Lambda 1 W1 plus lambda 2 W2. That's just this sum. This is your addition, correction term. And lambda 1 and lambda 2, some numbers to be found. We have to find them. So what we want this vector W3 to be orthogonal to W1 and W2. Okay, let's just take dot product. We can check this orthogonality condition. We check first dot product with W1. Yeah, and look, when you take dot product here, it's very easy to take dot product here because W1 dot W2 is 0. So this term disappears. We only get this. And this is we can compute. This is 2 plus 9 lambda 1. And then you do the same with W2. Then W2 dot W, okay, this is a type, it should be W. Dot W1 is 0, so we get only this. So we get 4 over 3 plus 4 over lambda 2. Okay, we found lambda 1, we found lambda 2. This gives us the third vector. So we now have three vectors, W1, W2, W3, which basically obtained as a linear combinations of vectors, original vectors U1, U2, and U3. So this is not important in this example, but in application it's important if you take vectors in some subspace. You always stay within the same subspace. You don't get out of the subspace. But now, instead of three basis vectors, you have three orthogonal vectors, which also basis, but it's good basis. It's orthogonal basis. So W1, W2, and W3, they are orthogonal. But this is not the best basis. The best is probably orthonormal. So this is done on the next slide, but this is basically scaling. You have the three vectors. This is almost what you want, with one exception. The length of these vectors are not 1. So the simplest way to get orthonormal basis out of these three vectors is just to scale them by dividing by the length. Okay, yeah, this is what basically we do. I call it sometimes you normalize this vector. So instead of vector W1, you consider W1 divided by the length of W1. You compute the length of W1 and you get this vector. Similarly, you take vector W2 and this one. You compute its length and divide by its length, and you get this vector. Yeah, and with W3. Now you have these three vectors, and you can check these guys, of course, are orthogonal because original vectors W1, W2, W3 were orthogonal, but also the length is 1, so they are orthonormal. Okay, good. This is called Gram-Schmidt process. It's very efficient, it's very fast, but when you do it by hands, it usually takes some time to compute. You see, even in this case, it took 3 slides. Okay, and now let me state probably the most powerful result of this lecture, which you can use a lot. It's super helpful. And in the future, next week, we will use this result to prove rank nullity theorem. Okay, it's called orthogonal decomposition. Again, we take linear subspace in n-dimensional space. We take its orthogonal complement, and then we have these three properties of orthogonal complements. First of all, that V and orthogonal complement to V intersect only by zero vectors. By zero vector. There's no other vectors in this intersection. Okay, this is good. Second, then every vector in the whole space in Rn can be decomposed as a sum of vector from V and vector from orthogonal complement to V in a unique way. This is crucial. Okay, and the third property, if you take a sum of dimension of V in orthogonal complement of V, you get n. Okay, think to get geometric idea what this proposition is, take a three-dimensional space and suppose that V as a, for example, plane. What's the orthogonal complement to a plane? Is just a line orthogonal to this plane. Yeah, plane passing through the origin. We want it to be linear subspace. And then this line also going to be passed through the origin. So if n is 3, if V is a plane in R3 passing through the origin, that orthogonal complement to V, it's a line, one-dimensional vector subspace of R3 passing through the origin. Yeah, and of course the intersection going to be just the origin. And it's intuitively clear, yeah, if you take in this space, in this plane, if you take the basis, for example, take some two orthogonal vectors, then the third vector in the orthogonal complement to V is just the cross product, yeah. So then you get three orthogonal vectors in R3 are going to be form a basis, and then every element can be decomposed as the sum uniquely. So say this is as vector in your plane, and this is vector in your line. Yeah, and finally the dimension adds up to 3. Yes, plane plus line. I mean, dimension of the plane is 2, dimension of the line is 1. You get 3. So this is give you a very good illustration. Yeah, extremal case of this illustration, if instead of V you take the whole space, for example, take V to be Rn, then orthogonal complement to V is 0, and then everything in this proposition becomes trivial. Yeah, okay. We're not gonna prove this, but we just gonna give you idea how to prove this, and the remaining should be checked by yourself, or please read in the lecture notes. All details for this important proposition can be found in the lecture notes. Here I only put the main idea of the proof. So basically, the main idea of the proof, how to find this vector V and this vector W. If you know them, you basically can prove the rest quite easily. Yeah, so this is just an idea. You take V to be x minus px, where p is this orthogonal projection, yeah, and W to be orthogonal projection. Yeah, that's it. So again, by definition, orthogonal projection is contained in V. So sorry, it's contained in okay. This is a typo. I just noticed. So this should be V and this should be W. Yeah, P should be element in V, and this vector should be vector W should be vector orthogonal to V. Yes. So this is the main idea. Of course, clearly the sum is X, so this is satisfied. You have to prove that this is unique. This is a bit delicate, but this is maybe the key point of the proof. And then also you need to check, this is has to be checked accurately that the dimension adds. But how can you do this? You can use the lemma about the orthogonal basis. You take the orthogonal basis of V, and then you take the orthogonal basis of orthogonal complement of V, and then by definition, they're going to be orthogonal to each other. So, so you just need to check that the number of elements in each of these bases adds to n. Yeah, that's basically it. And this is quite straightforward to prove because there's no vector which orthogonal both. If vector is in the intersection, it has to be orthogonal to itself. So it's only one such vector is 0. So this is basically the sketch, very fast sketch of the proof of this proposition from the lecture notes. Strong advice, as usually, try to prove this yourself. If something is not going to work, just read the proof from the lecture notes. Okay, let me stop the recording.